Lesson 5.3, Satellites. As the satellite orbits around its main body, gravity provides a centripetal force. So there is only one speed a satellite can have if the satellite is to remain in orbit with a fixed radius. Why only one speed? Well, centripetal force is mv squared over r. Gravity is providing that, so that is gmm over r squared. Make those equal to each other. The m's cancel, one of the r's cancel, and then just take a square root. So v will be the square root of gm over r, where r is measured from the center of the Earth or the center of whatever the satellite is orbiting. Let's calculate the speed of a satellite 500 kilometers above the Earth's surface. Now, if the Earth is here, we have the radius of the Earth plus the 500 kilometers. So the radius of orbit is the radius of the Earth, or 6.38 times 10 to the 6th meters, plus our 500 kilometers, which is 6.88 times 10 to the 6th meters, is our orbital radius. Well, v is the square root of gm over r. G is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. We're orbiting the Earth, so the mass would be the mass of the Earth, which is 5.98 times 10 to the 24 kilograms, all over our orbital radius, 6.88 times 10 to the 6th meters. Do that calculation, you get about 7,610, that's rounded to 3 significant figures, meters per second. That's moving pretty fast. So that's 7.5 kilometers every second. And this is actually one way you could figure out mass of the planet. Just observe the speed of a satellite that's going around it and use this to calculate the mass. Let's find the mass of a black hole where the matter orbiting it at the radius of 2 times 10 to the 20 meters moves at a speed of 7.5 million meters per second. Okay, so if our speed is the square root of gm over r, and we want m, let's go ahead and solve for the m. So I'll square both sides, multiply by the r, divide by the g. So that's our mass. The r, fill in our numbers now, the r is 2 times 10 to the 20 meters. Our speed is 752,000 meters per second, and that's squared. And the g is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And you multiply and you divide all that, and you should get 1.70 times 10 to the 44 kilograms. Very massive black hole. So again, for a satellite orbiting a planet like the Earth, the centripetal force is provided by gravity. So we have our centripetal force equals the force of gravity. Cancel the m's and one of the r's, and you get v squared equals gm over r. But speed is distance over time, so our speed is the circumference over the period. So we can plug that in for our v. And then square everything. So the 2 squared, pi squared, r squared, t squared. Do all that. Rearrange this, and you get Kepler's third law. T squared over r cubed is 4 pi squared over gm. And for circular orbits, we could rearrange it and multiply it by the r cubed. This gives us our relationship between the period and the orbital radius. Let's use the data of Mars to find the mass of the Sun. All right, so there's our radius, but we probably need it in meters, since that's what our constant is. Kilos times 10 to the third, so that would make it 2.279 times 10 to the 11 meters. Our period is in years. I probably need that in seconds. So 1 year is 365.25 days, because we have a leap year. And then 1 day is 24 hours. And 1 hour is 3,600 seconds. So the year canceled, the days canceled, the hours canceled. And so if we multiply all that together, we get 59359,845.6 seconds. Now obviously it's not going to be that exact, but hey, that'll work for this example. All right, so it's t squared over r cubed equals 4 pi squared over gm. Our t is 59359,845.6 seconds squared. Our radius is 2.279 times 10 to the 11 meters, and that's cubed. G is 6.673 times 10 to the negative 11 times m. So I think we can cross multiply those together. And multiply those together. And then divide, and we should get a mass of the Sun to be 1.99 times 10 to the 30 kilograms. Which, if you look up the data for the Sun, the mass of the Sun is 1.99 times 10 to the 30 kilograms. Hey, what do you know? Physics works. Since satellites are moving only under the influence of gravity, and the acceleration points towards the Earth, satellites are actually in free fall, just like in projectile motion or just dropping something. Astronauts in the space shuttles and the International Space Station seem to float. So they appear weightless. But they're not really weightless. There's gravity up there. They're being pulled towards the Earth. They're really falling. And the acceleration is almost the 9.8, I think we calculated is like 8 point something meters second squared towards the Earth. So why don't they hit the Earth? Well, because they're going so fast sideways that they miss the Earth as they fall. To describe this idea, I'm going to go to a book. It's called Dragonfly, NASA and the Crisis Aboard Mir by Brian Burrow. And we have one NASA astronaut, Leninger, and two Russian cosmonauts on the Russian space station Mir. And they need to go out and fix something up on the surface of the space station on the outside. So they're going out for a spacewalk. It says they were finally able to close and repressurize the hatch. Several months later, a new team of cosmonauts returned and found the hatch impossible to permanently repair. Instead, they attached a set of clamps to secure it in place. It is this set of clamps that Leninger and Tisblev are staring at uneasily 7 years later. To his relief, the commander opens the hatch without incident and crawls outside onto an adjoining ladder just after 9 o'clock. Leninger begins to follow. Outside, the sun is rising. The Russians have planned the EVA at sunrise so as to get the longest period of light. But because of that, Leninger's first view of the space is straight into the blazing sun. The first view I got was just blinding rays coming at me, Leninger told his post-flight debriefing session. Even with my gold visor down, it was just blinding. I was basically unable to see for the first 3 or 4 minutes going out the hatch. The situation only gets worse once his eyes clear. Exiting the airlock, Leninger climbs out onto a horizontal ladder that stretches out along the side of the module into the darkness. Glancing about, trying in vain to get his bearings, he is suddenly hit by an overwhelming sense that he is falling, as if from a cliff. Clamping his tethers onto the handrail, he fights back a wave of panic and tightens his grip on the ladder. But he still can't shake the feeling that he is plummeting through space at 18,000 miles an hour. His mind races. You're okay. You're okay. You're not going to fall. The bottom is way far away. And now, a second, even more intense feeling washes over him. He's not just plunging off a cliff. The entire cliff is crumbling away. It wasn't just me falling, but everything was falling, which gave me an even more unsettling feeling, Leninger told his debriefers. So it was like you had to overcome 40 years or whatever of life experiences that you don't let go when everything falls. It was a very strong, almost overwhelming sensation that you just had to control. And I was able to control it. And I was glad I was able to control it. But I could see where it could have put me over the edge. The disorientation is paralyzing. There is no up, no down, no side. There is only three-dimensional space. It is an entirely different sensation from spacewalking on the shuttle, where the astronauts are surrounded on 3 sides by a cargo bay. And it feels nothing like the Star City training pool. Leninger is an ant on the side of a falling apple, hurtling through space at 18,000 miles an hour, acutely aware what will happen if his Russian-made tethers break. As he clings to the thin railing, he tries not to think about the handrail and the command module that came apart during a cosmonaut spacewalk in the early days of Mir. Loose bolts, the Russian said. Loose bolts.